Push that rock with Simpson math. Let's talk about the mean value theorem. This is not a mean value as in one mean value like it's mean a Google or something. It's big and bad. No, this is mean as an average. Like if I want the average of 2 and 4, I go 2 plus 4 divided by 2 and get 6 over 2 is 3. Okay, that kind of mean. Okay, so mean or average value theorem. The hypothesis of the mean value theorem says f is differentiable over a to b. If it's differentiable, well, then it's for sure continuous, okay? But it's not only continuous, it doesn't have any kinks or any sharp turns up or anything that would ruin its differentiability. Let's draw that. So I got a and I got b, and I have some differentiable function on this. You know, that's differentiable. Looks like I could get the tangent for anything on this curve, okay? What conclusion can we get from that? Well, maybe a lot of them. So let's go ahead and look at the conclusion. So the conclusion of the mean value theorem says that there exists some element on the interval, so some element in the domain, such that, what is this? A weird thing here, that the derivative evaluated that value is equal to this. What's this? This looks like a slope formula. Doesn't it look like a y minus a y over x minus x? So let's back up and look at that. So here's a f of a. Here is f of b. Okay, and if I go this y value minus this y value, I'm getting the rise here. And if I go this x value minus that x value, I'm getting the run here. So what we're getting is the slope of a secant line. We're getting a slope of a secant line. Yeah, okay. And the theorem is saying that there's some value in the domain so that if you put it in the derivative, you get the slope of the secant line. So there's some value in here. And you know what? I think I was supposed to have open here. It's not A or B. It's somewhere strictly in between. Somewhere in here, there is a value that if I put it in the derivative, I get the slope of the secant line. That, if you put it in the derivative, you're getting slope of the tangent. So there's some place where the tangent is parallel to the secant. There might be several of them. For this particular drawing, I bet there's one in here somewhere that had the tangent as the slope, and one up here somewhere. About right. Let's see. It should be slightly positive, so about right there. You know. And then there's another one maybe right there, you know, so there may be several, but there's at least one. When it says there exists C, and that's guaranteeing at least one. So depending on how you draw the curve, there may be more than one, okay, or which curve you're dealing with. But there's for sure always, if you have a differentiable function over some interval, there's always some place where the tangent line is parallel to the secant line. Oh, that's interesting. Why do they call it the mean value theorem? Oh, well, the slope of this secant is the average slope over this interval. And so we're saying, the theorem is saying there is guaranteed to be a place where the instantaneous slope, the slope at a particular point, equals the average slope. Is that always true with averages? Well, no. Look right here. I had two numbers, 2 and 4, and their average was 3. So their average is 3, but there was no number in the set that was equal to 3. Well, this theorem is saying that there for sure is a tangent, a slope in here equal to the average slope. Okay, that's interesting, I guess. Now, there's a corollary called, this is a Frenchman, I don't know how to pronounce his name, Rolle maybe, or Rolle, I don't know. It's theorem. I call it the roller coaster theorem, as we will see. Why? Now, it's still hypothesis is f is differentiable over ab, but it tells us that f of a and f of b have to be the same thing. So I'll draw it where f of a and f of b are the same thing, okay? So f of a has to equal f of b in this corollary. Now, it's corollary, so it's an obvious result of the previous theorem. So I have a differentiable function here. All right, there it is. Now, I'm going to draw the secant. So draw the secant, because before we needed the secant. And what's it saying? it's saying that there must be a place where the tangent line is parallel to this. Oh yeah, maybe right there and right there. In this case, I have two of them, and there has to be at least one. That's the conclusion. There exists C in the domain such that the derivative evaluated at C will equal to 0. Oh, so if you can find a place where the function has two equal outputs, you have guaranteed that there is a place where the function's has a flattening out. Flattening out. Okay. So, where the derivative has a root. What we're going to do a lot is look for roots, like these two. Okay. And if we find two different distinct roots for a differentiable function, then we know there is some place where the curve flattens out and the derivative will be 0. We know that by the roller coaster theorem. Now, I do have to warn you that a function can have a 0 in its slope and not be a turnaround point. Look at this guy here. We would say right here at this value, the tangent is 0. It's perfectly flat. So you can have a situation where the tangent is 0, but the curve did not change direction. Notice it did not change direction. But frequently, when the tangent is flat, it does change directions. We do go from decreasing to increasing, or from increasing to decreasing. So, finding places where the derivative is 0 helps you find potential turnaround points, or what we're going to call local extrema. This is an extremum. Together, these two are extrema. Now, you have to watch out. It's not necessarily the case that it's an extrema. So this one's not. Just because the derivative is 0, the derivative of a was the derivative of this function. If this is f, then the derivative of this function at a would be 0. But it's certainly not a turnaround point. But here, this is a turnaround point. So c comma f of c is a point where the graph turns around. So you can see how we're going to use this theorem, but you have to be careful. Math made simple. It's Simpson Math.